Welcome back. In this video, we are going to talk about the half-life of a radioactive substance. Now, as the radioactive substance decays, it changes from one element into another. Like for example, if we have radium that decays to radon. Now, as the alpha particles, beta particles are given off, the radium is changing to radon, gradually is changing to radon. And the rate at which it's changing, it starts to drop because the number of atoms of radium left will become less. So as the decay goes on, there's less and less atoms of that substance remain. Therefore, the rate of decay decreases with time, okay? Because the rate of decay is proportional to the number of atoms present. The number of atoms that are present, okay, the rate of decay depends on that. Rate of decay is proportional to the number of atoms present. Now, so the radium will, the mass of the radium will decrease and decrease and decrease. Does that mean that eventually radium will disappear and there'll be no mass left? Well, that doesn't happen because what is happening is the radium is changing into radon. Okay, so as radium is decaying away, radon is building up. Okay, the radon is becoming more and more, and therefore the mass of the total sample will still be the same. There'll be hardly any difference. Now, we can, if we plot the graph of activity, which is the number of atoms which are remaining or which are left against the time, you'll find that the graph goes like this. It goes down and down and down because the number of atoms becomes less and less. Therefore, the rate of decay also falls. Now, we define a quantity called half-life, which is the time taken for half of the atoms to decay, is known as half-life. So we can find the half-life from here. Now, suppose there were 800 atoms to begin with. When the number of atoms comes to 400, that's half that amount. If we go across and we find the time it takes is called one half-life. And half-life is given by the red letters, like one half-life. When the activity falls from 400 to 200, it's halved again, and this is another half-life. Okay, the amount of time taken for each half-life is exactly the same. So we say that the half-life, so after two half-life, there'll be 200 atoms of radium left. After three half-lives, there'll be 100 left. Then after four half-lives, 50, and so on. So the fraction left, we say fraction is a half. This is half of a half, which is 1/4. Half of 1/4, which is 1/8. Okay, so we can say that the activity after one half-life, the activity is, it was 800 to begin with. Now, after one half-life is 400. There are 400 atoms left, and the fraction left is a half. Now, after two half-lives, this comes to 200, half of it, and the fraction is 1/4. Let me write these more on this side. 1/4. Now, which can be written as 1 over 2 squared. Now, after 3 half-lives, uh, the activity goes to 100 atoms left, and this is 1 over 8, which is same as 1 over 2 to the power of 3. Now, after 4 half-lives, this will be half of 100, which is 50. The activity will be half of 1/8. That means 1 over 8 and times the half, which is 1 over 16. Which can be written as 1 over 2 to the power of 4. Now, if we take n half-lives, I'll write this in different color. Now, we can derive a rule. The activity, the fraction that left will be 1 over 2 to the power of n. That will be 1 over 2 to the power of n. Where n stands for the number of half-lives. So after 5 half-lives, it'll be 1 over n to the power of 1 over 2 to the power of 5, which comes to 1 over 32. So what I'll illustrate this with an example. Now, if you say it takes 150 years, before we do the example, I'll just give you an idea of what half-life of different elements is. Now, uranium-238 has got a half-life of 4.5 billion years. That's a very, very long half-life. And radium-226 is 1600 years. Actinium-227 has a half-life of 21.7 years. And carbon-14, which we're going to discuss carbon-14 later on, has got a half-life of 5,700 years. Now, we can also make artificial radioactive isotopes, which are used in medicine and in industry, to have a much shorter half-life. Like, for example, iodine-131 has a half-life of only a few hours. It could be few days, few hours. So the half-life can range from billions of years to only a few minutes or a few seconds. Now, we take this for example. It takes 150 years for the activity of strontium-90 to decrease by 1 over 32 of its original value. What is the half-life? Now, we can say, I can use this rule. The fraction will be 1 over 2 to the power of n, where n equals 5. It takes... so, if we say one half-life, the fraction is a half, 2 half-lives is a quarter, 3 half-lives is 1 over 8, 4 half-lives is 1 over 16, and 5 half-lives is 1 over half of 1 over 16 is 1 over 32. Or we could have done this like 1 over 2 to the power of 5. That'll give me 1 over 32. That's 1 over 2 to the power of 5. Will give me 1 over 32. So that means the time elapsed is 5 half-lives. 5 half-life, it says what is its half-life. So 5 half-life is equal to 150 years. So we say that 5 half-lives equals 150. So how much is 1 half-life? 1 half-life is going to be 150 divided by 5. That's 150 divided by 5, which is 30 years. Okay, I'll write it down here. That's 30 years. So half-life of this radioactive substance, strontium-90, is about 30 years. Now, I'll do another example, okay? Now, if you want to try this by yourself, you can stop the video and try it yourself before I do it on the board. And the question is, it takes 150 years. No. No, actually, this question concerns carbon-14, and we use carbon-14 for carbon dating old bones or old pieces of wood. And you'll understand the idea. When the tree is living, it absorbs carbon dioxide, and there is a small proportion of carbon-14, which is a radioactive carbon, which is within the atmosphere. So the tree takes in carbon-14. So when the tree is living, its activity is fairly high. Now once it dies, and it starts to decay away. Now when it's decaying, its activity will drop, and depending on what its activity is now will depend on how old it was. Okay, and this is how we're gonna do this. If we have carbon-14 has half-life of 5,600 years. Now, if we take, this is example number 2. And the modern bone contains 80 units of C14. Okay. Old bone contains if a geologist dug out a sample of bone or wood from a site, and they want to carbon date it to see how old it is, okay, so they will measure the activity of this is 10 units of carbon-14. How old is the bone? So this is to find the date of the fossil, okay, how old it is. So if you want to try it yourself, you can stop the video and do the question, and then now I'm going to show you how to do this. Now, modern bone contains 80 units of carbon-14. Now we know that as present is 80 units. After one half-life, okay, one half-life it will be how much? Half of 80, which is 40. After two half-lives, it will be half of 40, which is 20. After three half-lives, half of 20 is 10. 10 units. So 10 units are left after three half-lives. That means this bone is 3 half-lives old, and half-life of carbon-14 is 5,600 years. So 3 half-lives so 3 times, no, half-life of carbon-14 is 5,600 years. Okay, so 3 times 5,600, that gives you 17,100. Okay, and that's your answer. So this piece of bone, this bone that we found in an ancient ruin, is 17,100 years old. Okay, and this is how carbon dating works. So we'll see you until the next video.